Okay guys, in this video we're going to look at an application of when we might want to complete the square to throw something into vertex form in order to more easily answer some questions that we're trying to figure out about the situation in a quadratic situation. Let's go ahead and take a look at this situation. It says, while marching, a drum major tosses a baton into the air and catches it. It says here that the height h in feet of the baton t seconds after it is thrown can be modeled by this equation here, h of t equaling negative 16t squared plus 32t plus 6. So first things first, I think it's always valuable when you talk about an application problem to talk about what our variables are. And I see two variables here, h of t, which is really like our y value, and I see t. And reading through this problem, what I notice is that our h here, h of t or h, is our height of this baton, and our t is a time. So if we were to actually kind of sketch out this situation here, which I do want you to do, this is most helpful here. We're going to say that our x-axis here, it's kind of like our t variable. And so what we're doing is we're expressing as a function of time in seconds the height of this baton in feet. And so the interesting thing about this is that this function, as long as we have a time to plug in, we can plug it in and it should tell us the exact height of that object. Whereas also, if I have the height of the object, we could go place that in for h, and we could go backwards and solve for the time, now that we're getting very proficient with solving quadratic equations. And so what I want to do is kind of consider what this might look like, given that we have some standard form equation here, and that our a value is a negative 16. And so what we're going to discover is that we have this really quadratic or parabolic path here that this baton is following, and so it also opens downward. It would look something like this right here. And so we can kind of illustrate that the baton, it goes up and then goes down. But what I want to be able to do is answer some questions about this. And so letter A here, let's just go ahead and read this critically. My question is, what is the initial height of the baton? Or we want to determine the initial height of the baton. So first things first, what we're being asked to determine is the height. Okay. So if we're getting asked to determine the height, likely then we should know a time that we're talking about. And so in this particular case, I want to point out this word initial. Initial means at the beginning. So at the beginning, in terms of time, when would be the time when we say right at the beginning? Not before you started, not after you started, but right when you started. And so you'll see that I point out here, when we say initial time, we say initial height, we mean that it's at time 0. So what I'm telling you here is that I'm being very nice by writing that the time is 0. Going forward, I'm not going to say that. I'm just going to say, go find the initial height. And I'm going to assume that you know that I mean that we're talking about at time 0. So the neat thing about this function is, if I know that the time equals 0, then what we could do is we could actually go plug that into our function for the time. And everywhere I see a time value on the right here, just like we evaluate functions, we're just going to go put in 0 seconds. And so what we're going to see is something pretty, I guess, profound here. When we work with equations like this, what happens is anything with a t at the initial time would drop out, because anything times 0 is 0, and anything plus 0 is just itself. What we end up with here is just 6. And so to answer this question here, we would say that the initial height is 6 feet. Initial height is 6 feet off the ground. This must be the time at which this drum major, or sorry, excuse me, the height at which this drum major tossed it at time 0. So one thing I want to do is I actually also want to go over to our graph here, and I want to illustrate this. Time equals 0 right when we're on the kind of y-axis here. And so when we plug in 0 for time, what we're actually doing, and I want to label this point right here, is we're saying that when we're at 0 seconds, we're actually 6 feet off the ground. So you can see that with our mathematical model here, at the initial time, when we talk about the initial height, we're saying really it's just the y-axis here, or the y-intercept here is our initial height. We can even list this here. Initial time, comma, height. Okay. So since each point does represent a time in seconds and a height, let's see where we can take ourselves with this next part of this question, which is find the maximum height of the baton. So we're going to see a lot of quadratic situations like this where things are tossed into the air. But when we talk about a maximum, of course, we mean it's this point where our function goes from increasing to decreasing. And the only place that happens on a parabola is at the vertex. So with the vertex, what I want to do is I would like to label this as a time and a height combination. And what we want to do is go find both of these things. Now my suggestion is that we actually take this function in standard form and we rewrite it into vertex form so that we could really easily see the values of h and k. So in order to find the maximum height, what we're going to do is we're going to take the function we're given here, h of t, which is this negative 16t squared plus 32t plus 6, and we're just going to complete the square to rewrite this into vertex form. So a little bit different than the last few examples we saw because we have an a value that is not 1 here, but very much the same in that we're still just going to move the loose constant to the other side so that we can make this a perfect squared trinomial. And so on the left we get our height minus 6 is equal to negative 16t squared plus 32t. Now as we do when we have when we have this expression here where our a value is not 1, what we're responsible for doing is factoring out this leading value here. So that's all we're going to do in this step. We're just going to take that negative 16, but we're going to put it out in front and really talk about what would be left on the inside. So of course we would have t squared here, and in particular a 1t squared, but we have t squared and 32 divided by a negative 16 here would be a negative 2, so we get negative 2t. And then what I'm going to do is I'm going to put in this blank here for our c value. So recall that our c value, of course, is always our middle term squared here, and given that my middle term is a negative 2, when I cut that in half I get a negative 1 squared, which is a 1. So I know that if I want this to be a perfect squared trinomial, I have to add 1 to this side, and I also have to add the same thing to the left side. The thing to remember here is that we actually have to add negative 16 times that 1, because we really did add negative 16 times this 1 over here. So on the left side, if we go ahead and carry out our multiplication, negative 16 times 1 is a negative 16. So we get a negative 16 and a negative 6. This is going to combine out to be negative 22 total. And on the right side, the fantastic thing is, of course, we have a factorable expression now. And not only does it factor, but half of our middle term is what belongs in this spot right here. And so we're going to say t minus 1, since half of our middle term here was this negative 1. So the only thing we have left to do is really, as we do with completing the square, and I'm just going to move my work over here, is we're going to say move that constant back over to the right, and what we end up with is this new equation that is really the same parabola when you graph it, but it's in vertex form as opposed to standard form. And so to look at this, what we want to indicate is that our vertex is actually at 1, 22 for our h here and our k here. And I'm also going to go label this on the graph. At 1 second, okay, we reach 22 feet in height. So to answer this question here, which I've sort of run out of room to answer, I'll try to block this off and I'll put it in this little space right here. But basically, we would say the maximum height, the max height, okay, would that be our x value or our y value at the vertex? And given that our x value is like time and our y value is like height, we would say that the maximum height here is 22 feet. And to answer the corresponding part of this question, find the time at which it reaches a maximum height. We're really just looking for the x value at our vertex here, which happens to be, in this case, 1 second. So we would say we reach a max height at 1 second. 1 second. Okay. So for the last part of this video, what we're going to look at is this last question here. And it's asking, if the drum major catches the baton when it's 4 feet above the ground, then how long is the baton in the air? So in this case, what you're going to recognize is I'm asking you for a time. I want to know at what time does it reach 4 feet in height. And so in order to figure this out, since we're given a height, what we're actually going to do is take our, I suppose, our vertex form equation here or our standard form equation. Either one, we're going to set the height equal to 4, and then we're going to work backwards to solve for the time. The thing here is, I feel like it's a whole lot more convenient to work with our vertex form equation now that we have it. So just to rewrite my vertex form equation where there's less, I suppose, other things written around it, here we had negative 16 t minus 1 squared plus 22. And so what we're saying here is let h of t equal 4 And then what we're going to do is we're going to work backwards to find out, well, then what the heck was this t? So because we can just plug and chug here, we'll put in our 4 over here for the height, and we'll say, hey, now let's go look for the t value that causes this to be true. And the neat thing about this is, because we're using the vertex form of the equation, we can just solve this using square roots, since we just have the parentheses here as our only squared term. We have no t to the first term. So when I look at this, to solve this, we'd have to get the squared quantity by itself first, by first subtracting 22 from both sides. So on the left here, what we're going to end up with is actually a negative 18, and on the right we get left with just negative 16t minus 1 squared. Now, don't make this mistake. You cannot distribute this through, okay, because we have a squared right here. What we're going to do is we're going to do the opposite of multiply by negative 16. We're going to divide both sides by negative 16. Now, because this is an application problem, most times I would be really nitpicky about leaving this in like exact values, but I'm actually working to get a decimal here. So this negative 18 over negative 16 here, I am actually going to reduce those both. Since it's a negative over a negative, we'll make it a positive over a positive, and I am going to reduce these both by a factor of 2, so I would get 9 over 8, but I'm very, very cool with leaving it as just 9 over 8, and on the right side then we'd have this t minus 1 squared. So solving this using square roots, okay, of course we would take the square root of both sides, and remember that because I'm not being nitpicky, I would like to have a decimal on this time, I'm just going to leave this as the square root of 9/8, and I'm not going to simplify it. Because what I know is, if I'm getting a decimal, plus or minus the square root of 9/8 is equal to t minus 1, and the only thing we have left to do is just add the 1 to both sides. So what we end up with is just t on the right, and on the left side I actually get 1 plus or minus the square root of 9 over 8. So now I'm going to put a box around this, and I will say that it would be a good idea to distinguish between these answers. One of them is, of course, 1 plus the square root of 9/8, and the other one is 1 minus the square root of 9/8. We're going to go ahead and evaluate for both of these on our graphing calculator. Here we'll just get a decimal, so I'll quit out of my graph mode here. So I'll turn on quit, and what we're going to do is we're going to type in 1 plus the square root of, okay, 9 divided by 8. Now I have to put the 9/8 in parentheses, so I take the square root of the whole thing, but here's my square root of 1 plus, my 1 plus the square root of 9/8, and when I hit second enter, I'm just going to go back and I'm going to pop this over to a minus here. What I want you to see is that we get 2 times, and I'm going to round to about the nearest hundredth of a second. So we get 2.06 and negative 0.06. I'm going to write both of these down. So we get approximately 2.06 seconds, since this is a time. We also get approximately negative 0.06 seconds. Now, with respect to this experiment, let's think about this for a second. How long was it in the air? Would it make any sense to tell us, or tell ourselves, that it was in the air for negative 0.06 of a second? And the fact is that it doesn't make any sense whatsoever. So to answer this question truly, we would select a more reasonable of these two values. We would say that it was in the air for 2.06-ish seconds. And looking back up here on the model, why are we getting 2 times a positive and a negative? Well, think about it this way. If we say that our initial height here is a height of 6, that would put a height of 4 at right about here. And so if we're saying we want to know what times did we reach a height of 4, then it was right here and right here. And so since we're really looking at time, you're actually, because we're using just a model of the situation here, you're going to get 2 times because it is a parabola. And we get a negative time over here on the left, that's our negative 0.06. And over here on the right, this is our positive 2.06 seconds right here. And so in terms of which one is more meaningful, of course we mean this one over here on the right. Cheers.